So we saw there are three possible phenomena which can occur in relation with the movement of electrons between energy states: stimulated absorption, stimulated emission, spontaneous emission. So we are going to look at them one by one now. We start with stimulated absorption. So the incident quanta of energy excites the electron from its equilibrium state, that is the original state at which it was, the stable state, to an excited level. So because it is going from a lower level to a higher level, we call it absorption. And because this absorption is triggered, like I said, by some incident energy, we call it stimulated absorption. Now we are going to write a mathematical expression to denote the rate of stimulated absorption. So experimentally it was determined that this rate of stimulated absorption depends upon the number of electrons in the lower state, in the equilibrium state, as well as the energy density of radiation. So let me explain this part. R12 stands for the rate at which stimulated absorption takes place. R obviously rate, and 12 to signify that the electron is going from a lower to a higher energy level. So that is the symbol for rate of stimulated absorption. It is directly proportional to the number of electrons in the lower state, because whatever electrons are present in the lower state, they are only going to shift up to the higher state. So obviously how much moves up depends on how much is initially there in your equilibrium state, and upon the energy density of radiation, meaning how much energy you are providing. So these are proportional. So when you remove the proportionality symbol and replace it with a constant, it was found that R12 equals B12 N1 rho of nu d nu, where R12 is the rate of stimulated absorption, N1 is the number of electrons in the lower energy level, rho nu d nu is the energy density of radiation, that is how much incident energy you are providing, and B12, called Einstein's B coefficient, is the probability of occurrence of stimulated absorption. Now why probability? Because see, what's happening in stimulated absorption is you have electrons at a lower level, you have a higher level also. You are providing energy, the electrons take that energy, they break free from their binding forces and they go to the higher level. That is what stimulated absorption is. Now stimulated absorption need not always take place, right? So when I give energy, it is possible that the energy I gave is not sufficient to break those binding forces. In that case, even though I gave energy, absorption is not going to take place. Or it is possible that the energy I gave is used for some other purpose, to make some changes in the lattice structure of the atom, or to remove some impurities or whatever. So the energy could be used in other ways as well. So you do not know that every time I give energy, and whatever energy I give, it is always going to help the electrons move from a lower level to a higher level. Not necessarily. So there is a probability that the energy I invest will be used for this purpose. So that is the proportionality constant. So the probability of occurrence of absorption times the number of electrons in the equilibrium state times the energy density. So that is stimulated absorption, and it leads to increase in the population of the higher energy state, obviously, because the electrons from the lower state are going to the higher state, the population there is going to increase. Now what happens to the electron in the excited state? Like I said in the previous segment where I was giving you an overview of the three processes, the electron which goes from a lower state to a higher state cannot stay there forever, because the higher state is highly unstable. So at some point or the other, the electron is going to find it too difficult to handle that high energy, and it is going to come back to its equilibrium state. The time it spends there is called the characteristic time tau, or the lifetime of that energy level. So if an electron from E1 goes to E2 and spends say 5 milliseconds there and comes back to E1, the characteristic time or the lifetime of E2 is 5 milliseconds. This relaxation or this coming back again can be because of radiative or non-radiative means. Radiative meaning stimulated emission, where I again provide some energy, and thus I encourage the electron to give out its energy and come back. Or non-radiative meaning the electron itself finds E2 too unstable to remain there, of its own accord it gives out energy and comes back. So that is radiative and non-radiative. So the emission in general can be because of either one of these reasons. So the lifetime, generally we take it to be a sum of the non-radiative and radiative lifetimes.